processing. I'll start again. Welcome to our invited lecture on natural language processing. Today's speaker is Prof Pushpak Bhattacharyya, who is a professor at the Department of Computer Science and Engineering at IIT Bombay. He has done extensive research in natural language processing. I've been one of his students, so I can quite clearly vouch for it. He has more than 350 research papers and around the same amount of PhD, masters, and undergraduate students graduating from under him. He is also the fellow of National Academy of Engineering, Abdul Kalam National Fellow, a distinguished alumnus of IIT Kharagpur in India, and ex-president of the Association for Computational Linguistics. So, thank you all for attending the talk, and may I welcome the speaker, Prof Pushpak Bhattacharyya, please.
So I hope I am audible.
Yes.
And also to online audience.
The microphone is not capturing. Is it work? Yeah, tap the mic.
Hello.
Yeah.
Okay, so good afternoon everybody, and thanks to Professor Constantine for inviting me and giving me this opportunity to talk to you about our research in natural language processing. I would also like to thank Ditesh for all the help and the organization. Thanks to IME and Leonardo for all the logistics support. Now, the title of the talk is Alice in Wonderland, Navigating the Landscape of Multilinguality for NLP. This talk is on multilinguality, okay, the interaction of many languages of the world, how languages can help each other in their computation. And we appeal to the imagery of this famous book by Lewis Carroll, and the famous character called Alice, who is a little girl and who finds herself in a strange land with many phenomena, many characters, many events, including a rabbit, including a Cheshire cat, and so on. And I would like to say that our journey in this world of natural language processing, containing many languages, is also like that of Alice, who is wondering at many different sights and sounds, impinging on her senses and looking at the world around her. So the world of natural language processing is indeed wonderful, with very challenging and more importantly useful problems like machine translation, question answering, sentiment and emotional analysis, information extraction, information retrieval, and so on. And all these tasks, which have been done for decades for English, are now becoming very important for other languages of the world. Now, the reason for that is that the world is pretty multilingual. But if you sort of allow me, before we go ahead, this is one small poem I wrote. Okay. This is called Ode to Scientists and Engineers. It reads as follows: Scientists ask why, engineers ask why not. Scientists wonder at what is, engineers wonder what could be. World couldn't do without either. Scientists study, engineers make, and ever the twain shall meet. Now, the reason for mentioning this point to you is that we need both insight and implementation. In this world of data and machine learning, linguistic insight and insight into the task at hand are sadly missing, but we understand that they are very important, especially for two things, especially when we create annotated data and we have to find out what the annotation should be. This requires a very intricate interaction between linguistics and computation. And then when we do error analysis on the output of the built model, that too needs sort of language insight and task insight. Now, the reason for multilingual computation becoming important is that the world is multilingual. English is a very important language, no doubt, but there are linguistic realities all around us. And we see that Bing Translator supports 103 languages, Google Translator supports 109 languages, and another 126 are under development. So the importance given to multilingual computing is indeed very big in today's world. So I come from a country which is really multilingual in nature. The map here shows many different states of the country, and there is a tremendous amount of linguistic diversity, which I'll mention as we go ahead. Now, languages in the virtual world also are very diverse and very numerous. So, if we look at the distribution of languages in the world of Wikipedia, then of course English leads the pack with about 6 million articles, corresponding to about 54 million pages. Now, German, French, and Spanish belong to the 2 million articles club. Japanese, Chinese, and Arabic belong to, let's say, 1 to 1.5 million articles club. When we come to India, Urdu is the language with maximum number of articles, about 165,000. Hindi, Tamil, and Urdu are similar to one another in terms of their number. Marathi, Malayalam, and Telugu belong to the 70 to 80,000 articles club. Nepali, Gujarati, Kannada are in 30,000 group, and Oriya has about 15,000 articles. Okay, so all these textual content are real; they exist in the virtual world, and they need processing. Now, when we go to the linguistic typology, okay, the typological classification of Indian languages, there are 4 families in the country. Indo-Aryan, which is spoken in the northern part of the country. Dravidian in the southern part. Austroasiatic, there are 2 languages, Khasi and Munda, and Tibeto-Burman, which is in the northeast of the country. Now, within the Indo-Aryan family, we find subfamilies, and some of the languages are very prominent. For example, Punjabi, Gujarati, Hindi is probably Hindi, Urdu are together form the 4th highest number of speaker population speaking that language. Marathi, Bengali are also within 20 in terms of their speaker population. Now, let me take a quick look at our journey in this world of multilingual computation for about the last 25 years. Our natural language processing activity started with what is called the UNL project. And that was interlingua-based machine translation. Interlingua-based machine translation demands complete disambiguation of the source text. And that really requires a lot of disambiguation in terms of named entities, phrase structure, lexical disambiguation, and so on. So since disambiguation became important, especially at the word meaning level, we created Indian language Wordnets, of which I'll give a demo very quickly. We applied these Indian language Wordnets for cross-lingual sentiment analysis. Now, this was pre-word embedding days. Okay, we navigated into the meaning space through Wordnet senses and did multilingual computation. Now, same emphasis on multilinguality led us to investigate what is called multilingual pseudo-relevance feedback. I'll give some details on this work as we go ahead. Multilingual words and disambiguation has always been a preliminary, primary concern in our NLP activity. We reported work on pan-Indian machine translation in the statistical MT setting. We can take help of pivot languages again in a multilingual setting for high accuracy machine translation. Then continuing multilingual named entity recognition, was reported, multilingual transliteration was reported, code mix question answering. We did quite a lot of work in this. Now, pan-Indian neural machine translation is our recent activity. We try to investigate the utility of natural language processing for mental health tracking. And of similar kind is adverse drug reaction tracking on the social media posts that patients talk about when they take a drug. Multilingual annotated data was released in recently concluded LREC. Speech-to-speech machine translation, we are part of a very large Government of India funded project. And there we study text-to-speech, disfluency, and these kind of activities. And multilingual aspect-based low-resource sentiment and emotional analysis is a piece of work which is under review now. So this really covers a large landscape of natural language processing, always keeping Indian languages and many other languages in focus, which is a multilingual computational work. Now, maybe for some of us, it may be useful to look at the nature of natural language processing. Natural language processing is art, science, and technique of making computers understand and generate language. Now, this way of doing NLP is very well established. This is called the NLP stack. We start with the morphology, that is processing of words at the lowest level, and go up to large pieces of text, which is discourse, co-reference, pragmatics, and so on. In between, we have a number of very crucial NLP tasks involving meaning extraction, which is semantics, syntax, which is parsing, and also shadow parsing. Now, NLP is at least a three-dimensional task where the problem, the language, and the solution, this combination becomes important. What works for English does not necessarily work for other languages. For example, the part-of-speech tagger for English will not work directly for Marathi, where there is a lot of agglutination. Many morphemes are stitched together to form a long word. So we need some segmentation and adjustments of that kind. Now, the main challenge in natural language processing is ambiguity. Words, phrases, sentences, all of them have ambiguity. I'd like to give you a real conversation which happened on WhatsApp. And it is very interesting to note how ambiguity arose as a concatenation of different factors. So there is this conversation between Lady A and Lady B. Lady B happens to be my wife, and she permitted me to use this example in my class presentation and so on. So Lady A and Lady B both are English educated, and they use code mixing freely. So both are Bengali native speakers, so they use both English and Bengali freely. Now Lady A asks, yesterday you told me about a shop that sells artificial jewelry. Ki naam jano. So this is a Bengali string which says, what did you say the name was? So Lady B wrote on WhatsApp, NYKAA. Then Lady A got very offended and said, what do you mean, madam? Is this the way to talk? Then Lady B is very surprised. She says, Kano ki bolo? Why, what happened? Now, what is the reason for this communication breakdown? The reason is this. There is a fashion shop called Nykaa, NYKA, which is a very famous industry in India, and they are doing very well also. Now, because of some curious coincidence, Nykaa is also homophonous with a Bengali word, Naka, okay, which means a pretentious person, and a person who, feigns ignorance, and this is a derogatory word. Now, a named entity, it became homophonous with a Bengali derogatory word, which is an adjective. Okay, and because both the ladies are English educated, and because they use Bengali, this concatenation of circumstances led to ambiguity and breakdown of communication. So this situation is not really a one-off situation. Okay, this kind of ambiguity noise is all around us, and it is really a marvel of human mind that we are able to process language so effortlessly. Now, Let me go into some of the resources and techniques in a multilingual computing scenario. In the Wordnet is a linked structure of 18 Indian languages with Hindi as the pivot language. Okay, all other languages Wordnets link with Hindi in terms of what is called the synset ID. Divtesh contributed a lot to this lexical resource, and this is an extremely useful language resource. So let me give you a small demo, if possible. So the screen is confusing. Okay. So let's take
What's it right?
what's that? Very exact. Yeah. So suppose we take the word lecture. This is in English. And lecture has 5 senses. The first sense is something which is familiar to us, a speech that is given to public. And I can see it in multilingual framework. So a lecture in Hindi व्याख्यान, आख्यान, अभिभाषण, lecture, and so on. I can see it in, it's in Nepali. I can see it in Tamil, which is a language from southern India, and so on. So this is a very useful resource for multilingual computation, which is created completely by us, Happy Ratio, for 18 languages of the country. This was a lot of work.
PowerPoint.
Yeah. Yeah. So let me continue. So this resource was found to be very useful in the following challenging words. So one of the tasks we undertook was unsupervised word synthesis disambiguation using in the Wordnet. This was pre-deep learning days, and cross-lingual word embedding, multilingual embeddings, these did not exist at the time. But we thought we will operate in the meaning space rather than the word space, and this afforded us a technique for multilingual unsupervised word synthesis disambiguation. So suppose we take 2 languages. In this case, it is Marathi and Hindi, which are close languages. The concept involved is a boy, okay, a male young person. So this has mulga, porga, por, the 3 words in Marathi, ladka, balak, bachcha, and chora in Hindi. Now, when we want to do disambiguation, then we first cast it in a probabilistic framework. So we take as an example the word man from Marathi, which has 2 senses. One of the senses is prestige, the other sense is neck, which is a part of the body. Now, the probabilistic formulation is that we compute the probability of the sense given the word, and whichever sense has highest probability is the winner sense. Now, this obviously requires a corpus which is annotated with senses, but we say that we are doing it in unsupervised framework, and there is a nice idea which is based on expectation maximization. So what we do is that we express the probability of the sense in Marathi in terms of the probability of the sense in Hindi. Okay, so we express the probability of man, the first sense of man, in the sense of gardan, which is neck in Hindi, and similarly we express probability of the Hindi sense of gala, which is neck, in terms of Marathi. Okay, so this kind of coupled expression of probabilities is possible, and when we initialize the probability values and iterate in an expectation maximization algorithm manner, we are able to obtain the senses of the words. And evaluated on some standard data set, we could see that we achieve an accuracy of about 70% in two domains, tourism and health. So these values were more than the most common baseline in words and disambiguation. This is Wordnet first sense. So we could cross that baseline by a very comfortable margin of about 20 points, and that gave credibility to the approach. Now the heart of this system is bilingual, okay, assistance between two languages, and that has been possible because the languages have linked wordnets. So this was a very nice piece of work where we could sort of sense that in a multilingual world, the languages can help each other. And if we can formulate the problem as a kind of expectation maximization, probability computation in Marathi can be looked upon as M step, probability computation in Hindi can be looked upon as the E step, and then it is possible to converge to the correct sense of the word in a completely unsupervised manner. The only resource required is linked coordinates. So we proceeded and wanted to see what else we could do with this linked structure of coordinates in pre-word embedding days, pre-cross-lingual word embedding days. So now we wanted to apply it to Indian language sentiment analysis. So sentiment analysis is defined by this 5-tuple. E is an entity, F is a feature, S is the sentiment, H is the opinion holder, and T is the tag. So this kind of precise formulation of sentiment analysis as a 5-tuple problem is important because of the following reason. If we have a sentence like, I love the songs in the movie, though only the cast was liked by my brother, who said the director is of the opinion that the storyline, which is from a novel by Shakespeare, will be lapped up by the public. There are many entities, many opinions, many features, and we can group all of them together to say, I love song, brother likes cast, director likes storyline, public lap of storyline, and so on. So this is an information extraction task, which is a pre-processing step for sentiment analysis. So since 2000, we have been working on many different sub-problems of sentiment analysis. Rule-based era, classical machine learning-based approaches, deep learning approaches now, and then combination of these approaches. Okay, so we've looked at many different problems of sentiment analysis with three generations of computational techniques. Now, what we found is that when we operate in the meaning space, then the sentiment analysis figure, which is based on words, okay, the words provide the signals for sentiment analysis. For that data, the accuracy was about 85%, which moved up to about 86% when we applied the senses of the words. And we do the modeling using Wordnet senses. So the accuracy improvement is not very impressive. But what is impressive is this. When we take Marathi language sentiment analysis, okay, pretending as if it was Hindi, okay, the data is the training is on Hindi, but the testing is on Marathi. Okay. In that case, we found that when the training and target language are both same, that is Marathi, then the accuracy is about 93%. But when we test on Marathi through the linked wordnet of Indian Marathi, the accuracy is about 84.5%. There is a fall of maybe about 10 points, but accuracy of 84.5% is still respectable in sentiment analysis. And this is what is called today the zero-shot learner. There is no training data for Marathi, and the accuracy figures are obtained using a Hindi trained model. Okay, so this is another indication that languages can help each other. So we continued this theme, and we wanted to investigate what can multilinguality do for a problem from information retrieval. This is called multilingual pseudo-relevance feedback. So pseudo-relevance feedback is a kind of query expansion technique. So that the information seeker presents a query to the search engine, and relevant documents come out from the search engine. So what is important is the ranking. So the relevant document should really be high up in the list of retrievals. Now, ranking itself is a function of the coverage of the information, the correctness of the query processing, and output presentation. Now, in coverage, crawling, stemming, these play an important role, whereas correctness of query processing is a function of stemming, named entity recognition, and multi-word extraction. So, we created India's first search engine where the queries were in Indian languages and retrieval was in Hindi, English, and that Indian language. So this was a large pan-India project involving many languages, where named entity recognition, stemming, multi-word extraction had to be done for about 15 to 16 languages across the country. Now here, an important technique in information retrieval is what is called pseudo-relevance feedback, where the pages are retrieved and then keywords are extracted from this first level of retrieval. Those keywords are fed back into the query, and that typically improves the ranking quite a lot. Now, what we asked is that when we do this pseudo-relevance feedback, why not go multilingual? Take the pseudo-relevance feedback from other languages. So we investigated this problem. So the framework was, the query was in language L1. L1 is translated into L2. Retrieval is done for both L1 corpus and L2 corpus. And then the L2 corpus's keywords are translated back into L1 and they are added to the query. So in this case, the pseudo-relevance feedback is not only from the language itself, but also from another language, which we call as assisting language. So this pseudo-relevance feedback we found could improve the performance of the search engine very remarkably. Okay, so multi-PRF actually showed gains for all parameters, okay, for the test purpose that we use, which was very standard. Now, I'll like to give you a few examples of the qualitative evaluation. So, if the query was Oscar, okay, Oscar honorific pour de réalisateurs italiens, okay, honorary Oscar for Italian filmmakers. So, in this case, the normal pseudo-relevance feedback did not capture all other terms which are important for this query. So, it actually drifted to misleading pages where irrelevant pages also came up. But the retrieval became much more focused and much more relevant when we translated this into English, and the pseudo-relevance feedback came from the English pages. So there, film, then all film-related terms got added to the query. So the map score precision at K, all these values improved, and it was clear that another language is helping. Now, we also asked if one language can help the information retrieval, why not multiple languages? So there we saw that if we bring in other languages, not only English, that too can help. For example, there was this query in German, bronchial asthma, and we translated this into Spanish. Here, a very important word which was missed in normal several levels feedback came because of multilinguality. That word is allergy. So allergy did not get added to the query by way of expansion in normal several levels feedback. It came from another language. Okay, so this is another example where we see that multiple languages can help each other. Now, we also ranked the languages in terms of their assisting capacity. So for English, we found that Spanish was the most prominent assisting language. For German, it was English. Now, German and English is intuitive. They belong to the same family. This is called the Indo-Germanic family. Why Spanish was helping English was a kind of mystery for us, because Spanish belongs to what is called the Romance languages. Portuguese, Italian, Romanian, and Spanish, French, they belong to the same language. Now, Spanish was helping English because Spanish had the largest amount of corpus and it was also very clean. Okay? So that shows the importance of high quality annotated corpus when it comes to natural language processing. So we proceeded with this theme of exploiting multilinguality in various NLP tasks. Then we moved to low resource machine translation. Now, machine translation is very important for a country like India because of the diversity of languages, and the kind of MT that needs to be done there is low resource. Okay, we do not have huge amount of parallel corpus, but we have been in the research of machine translation since 1996, where we got an interlingua based machine translation project from the United Nations. Now, machine translation can be divided into knowledge-based approach and data-driven approach, like many other machine learning problems. Now, in a knowledge-based approach, we have rule-based machine translation. Okay? And in data-driven, we have similarity-based machine translation, which is analogical machine translation. Then probability-based machine translation, which is statistical machine translation. And then today, neural machine translation. So EBMT, SMT, and NFT are data-driven, whereas RBMT is based on rules. The rules are created by human beings. Now, we also realized that in rule-based machine translation, analysis plays a very important role. In example-based machine translation, it is analogy, which is at the heart of things. And in statistical machine translation, it is word alignment, which is the foundation. And neural machine translation, attention plays a very crucial role. So it's a matter of interesting coincidence that in all these paradigms, there is an A word, okay, which is the crux of the matter. Now, we conducted this investigation of machine translation in low resource setting for many Indian languages. There were 10 Indian languages and English. They belong to the Indo-Aryan and Dravidian families. In Indo-Aryan, we have Punjabi, Hindi, Gujarati, Bengali, Marathi, and Konkani. In the Dravidian group, South Indian family, we have Telugu, Tamil, and Malayalam. Now, the Dravidian languages, the main property of Dravidian languages is that they are very agglutinative in nature. That means many morphemes are joined together to form long strings. So you can see here that there is a clear division in terms of accuracy figures. Within the Indo-Aryan family, when we do word level translation, the accuracy figures or blue scores are typically in the range of 20 to 40. So, for example, for Punjabi and Hindi, the accuracy figure is 69.97, about 70 blue score, which is very high. And this is for a test purpose which we have carefully cleaned and used for our experimentation. But when we go to the Dravidian family, that is inter-family machine translation, so Hindi to Tamil, the accuracy figure is only 11. Okay, so Hindi Punjabi is in the range of 60 to 70, Hindi Tamil is in the southern part of the country. The accuracy figure is only 11. Okay, there is huge amount of difference between the two cases. Now, we realize that this happened not only because the regular languages are complex in terms of morphology, but also because the resource was in short supply. So what happens when the morphology is complex? When the morphology is complex, many strings do not appear in the training data. And when they do not appear in the training data, what should we do? Because we have not seen such evidences in the training data. So we thought that we'll make use of subwording for artificially boosting the resource. So you can divide the words into characters, morphemes, syllables, orthographic syllables, and what is used in today's neural computation is byte pair encoding. That is the substrings which are statistically significant. So this is a word, jaunga, which means I will go. This can be divided into consonants and vowels, or consonant vowel combinations, or syllables, or orthographic syllables which end in vowels, and byte pair encoding where the substrings are very frequent. So when we make use of morphology analysis and use morphological segmentation on the training data, we see that the accuracy figures improve for all pairs. In particular, let's concentrate on Hindi Tamil. The value was something around 11, and this has improved to 12.94. The percentage improvement is 12.72. Okay. Then Hindi Malayalam was 9.8. Hindi Malayalam has risen to 9.86, which is about 16% improvement. So here the words are broken into their suffixes and their lemma. That is the minimal task which is done. So when we make use of byte pair encoding, where we have statistically significant substrings, then Hindi Tamil improves to 13.94, that is 21% improvement. Hindi Malayalam goes to 11.15, that is about 31% improvement. So this very significant improvements were observed when we make use of subwording. And subwording idea, all of you recognize, has been used extensively. Let's say in fast text, for example. Okay, so in word embeddings, which are created out of the word parts and not the whole words. So this showed us again that multilingual computation can benefit from common substrings, and we will show its impact again in unsupervised neural machine translation. So in multilingual machine translation, of course, a very important idea is pivot-based machine translation, where a third language comes and helps the translation of two languages. So here is an example. We have the word pani, which is in Hindi. The Bengali translation is jal. So now in Hindi to Bengali machine translation, suppose we do not have any evidence of pani translated as jal. There is no such evidence in the training data. But we have parallel corpus, small amount of parallel corpus between Hindi and English. So what pani gets translated into water, water gets translated into jal. So this way of doing machine translation through a pivot language is called triangulation. And here, the main idea is a basic law of probability, the probability of marginalization. We can introduce any number of random variables in a probabilistic expression, provided we do marginalization, that is, we take the summation over all possible values of the random variable. So this theory is worked out, and we used the triangulation approach where we had a source to pivot parallel data, which produces the phrase table, then pivot target phrase table, and source to target phrase table, if we have any small amount of corpus between two languages. So this is really a resource constraint scenario where help comes from a third language, okay, whose resource is slightly bigger in size. So such experiments we conducted for an interesting case of Mauritian Creole to English machine translation. So we had very little parallel corpus here. There was a postdoctoral scholar coming from Mauritius who was interested in this task because their government wanted to create this system, Mauritian Creole to English. Now here we decided that since the parallel corpus is in short supply, just about 25,000 sentences, why not use pivoting? So there, both linguistics and corpora came to help. Mauritian Creole is linguistically very close to French. And English to French is a high resource language. We have huge amount of parallel corpus for English and French. So we decided to harness French as the pivot language. And when we did that, we found that the accuracy improved by significant amount, especially for short sentences, short Mauritian Creole sentences. So if French could really help here, and the same observation could be replicated for English Hindi machine translation, where the pivot languages were many different Indian languages. And we found that Hindi Urdu as a combination language, Punjabi and Urdu, these two together could boost the accuracy very significantly for English Hindi machine translation. So if the accuracy figure was fixed, the corpus size reduced. If the corpus size was fixed, then because of pivoting, the accuracy. Okay, so this was again an extensive experimentation reported in top conferences in NLP, and this established the use of pivoting as a solution for low resource machine translation. So this idea we also pursued in neural machine translation. Now we come to neural machine translation, which is a ruling paradigm today. And I'd like to spend a little more time here going into a few more details because this is a ruling paradigm, and neural machine translation is an interesting case because it is so data hungry, and we want to apply neural machine translation for a low resource setting. So is this an oxymoron? Is it possible at all? Okay, can neural machine translation be done in low resource setting? So let's investigate. We went directly into completely low resource setting, which is unsupervised neural machine translation. No parallel corpus at all. Okay. So this study was conducted in 2019, and the background was that we made use of the cross-lingual embedding available in many different platforms. Okay, the technique of RTT, the technique of LAMPL, which are now well established for cross-lingual neural embeddings, was used. So the main framework is this. This is also now standard in unsupervised neural machine translation. We have one shared encoder and many different decoders for different languages. And we have fixed cross-lingual embedding at the encoder side. Now, two important techniques are used here. These are denoising and back translation. They also have become standard techniques in neural machine translation. Roughly speaking, denoising teaches the machine translation model the syntax of the language, and back translation teaches the vocabulary, very roughly speaking. So in denoising, what happens is that we permute sentences and insist that the model produces the correct word order. So the input is a permuted sentence, output is the correct sentence order. So when we present these for many different sentences multiple times with all kinds of permutation, the system acquires the knowledge of the syntax of the language. Okay, notice that we are teaching the machine translation model the syntax of the language purely through permutations. Back translation. Let us remember that in case of unsupervised machine translation, there is no parallel corpus. So what we do, we make use of this architecture. We have a shared encoder and many decoders. So if we have monolingual corpus of, let's say, Hindi, Bengali, Marathi, Gujarati, many different languages of India, then we can work with cross-lingual embeddings of these languages. Okay. And then send the sentences of one language and obtain the target language outputs at many decoders. Maybe they are of bad quality, maybe they are of inferior quality, but the translations which are obtained, they are again fed back into the system. Okay, so that is a back translation, and back translation is obtained from the monolingual corpus. So I hope the main idea is clear here. The first of all, the words are taken into a uniform embedding space, okay, for many different languages, and we present the input sentence at the shared encoder. We obtain the outputs from many different decoders for many different languages. Okay. Now we obtain what is called a pseudo-parallel corpus. Now in pseudo-parallel corpus, the target language sentences are again fed back into the encoder, and we apply computation based on this framework. So without going into many details, let me talk about the performance of such a system. It was reported in ACL 2019 with these European languages, and later we replicated the task for Indian languages too. So for French English, it is completely unsupervised, zero parallel corpus. The blue score was 14.47, Spanish English 15.45, English French 13, English to Spanish 14, German English 11.94, English German 8. So these were the accuracy figures. We also conducted qualitative observations. So for example, if you take this sentence here, which is a French sentence, the English reference is preparation to manage a class in a North American and Cuban context. So the bilingual baseline system with zero parallel corpus gave complete trash. Okay, the build up to manage a class in Australia and Australia. This was the output. But for a multilingual denoising back translation based cross-lingual embedding based system, we got a reasonable quality output. The preparation to handle a class in a Latin American context. The next sentence is also French, and there is going to be a change in how we pay these taxes. There will be the change in the course of whom we owe these bills, not making very good sense. There will be the change in the way we pay these taxes. This is quite good, almost perfect. Of course, there are many bad transitions also, but multilingual unsupervised setting where cross-lingual embedding is exploited could show interesting results. Okay. Now the next idea we followed up with is unsupervised neural machine translation with filtering on the back translation. Back translation generates what is called the pseudo-parallel corpus. What we asked is that if we apply filtering on the pseudo-parallel corpus, which is back translated, then if we filter in high-quality parallel corpus, can the system be performance be improved? Again, we'll not go into a lot of details here. The central idea is that filter the back translated data by giving more weight to good pseudo-parallel sentence. So what do we mean by good? Okay, so we modified the cross-entropy based standard loss function by adding a weight, this WB, okay, is the weight, which is based on the blue score. Okay, it's a kind of feedback. Blue score, which is obtained from the reference translation. So the loss function included a feedback from the blue score from the reference translations. And this could filter out bad quality back translated data. So again, there were baseline systems, Lampel and Ponyo and Son et al. And we could demonstrate, accuracy figure improvement, which satisfied test of significance. Even if it is by small amount, it was an indication that here is a technique which can help in unsupervised neural machine translation. So this was based on the fact that the blue score coming from the reference translation was integrated into the loss function. Recently, this year itself, we had reported our research on unsupervised neural machine translation with simple measures of bridging the lexical divergence. Okay, so one of the challenges of machine translation is lexical divergence. the other challenge is syntactic divergence. The word order may change, just like word goes to the end for Indian languages. The lexical divergence is vocabulary mismatch. Okay. Now, lexical divergence mismatch we could close by some simple measures. We tested these ideas on a number of popular models like XLM, mass pre-training, BART, and MBART. MBART is multilingual BART. So the simple ideas were script conversion, transliteration to a common script, unsupervised bilingual embedding-based initialization, and dictionary word substitution. Very simple ideas, and they're all very low in terms of computational complexity. So the monolingual data was coming from Bengali, Gujarati, Hindi, Malayalam, Marathi, Tamil, and Telugu, covering most of the important languages of the country. So Tamil and Telugu are from South India, Malayalam is also from South India, Bengali, Gujarati, Hindi, and Marathi are from the northern part of the country. We also tested these ideas on European languages, which is Czech, English, Estonian, Finnish, and Lithuanian. Now, the test and validation data, they came from the standard forum, which is WAT forum, and ILCI is a good quality parallel corpus data, about 100,000 sentences for many different Indian languages. We have also used this use test 2018, 2017, which are very standard data sets for machine translation testing. So now we look at the results. So first, for language pairs with high lexical overlap. Now, Hindi, Marathi are descended from Sanskrit. They have lots of common words. So Chandrama, for example, which means moon, exists in both Hindi and Marathi. So we first had the original script, and this is the baseline figure. Now, through a series of these simple ideas, simple transliteration, simple dictionary substitution, going into the cross-lingual embedding space, okay, again, how all these techniques are used, those details I'm not going into, we could finally achieve, these respectable figures of 8, 12, and so on. So this is in completely zero short setting. No Hindi Bengali, no Bengali Hindi parallel corpus. But still, accuracy figure of about 8 and 12. Similarly, for Hindi Gujarati and Gujarati Hindi, Hindi and Gujarati are also very close languages with high lexical overlaps. Many words are common between the two languages. Now, language pairs with low overlap. So Hindi, Malayalam, Malayalam, Hindi, very little vocabulary overlap, where they belong to completely different families. Hindi, Indo-Aryan, Malayalam, Dravidian, and Hindi, Tamil, Tamil, Hindi. So here also you can see we get blue score of 1 and blue score of 0.94 and 2.56. Okay, these are of course not at all useful blue scores. What do you do with blue score of 1 or 2? But still, compared to these extremely low baselines, we could still achieve some improvement, which is why possibly Cooling took that paper. While for closed languages, the accuracy figures were respectable. 8 10 is workable accuracy figures. Languages without any overlap showed these blue scores of 1, 2, and so on. So these showed that it is important to recognize the difference of properties between languages when they come from different families, especially when their vocabularies are extremely different. Okay, there some amount of semi-supervised, technique is required. So now we did some qualitative analysis also. This was for Bengali and Hindi. The Bengali input sentences, the board of trustees of Hanogi Mahamandir, which is a temple, organizes many activities in Navratri. Navratri is a festival in India. So the reference translation is shown there. Hanogi Mata Mandir Nyas Navaratri में अनेक कार्यक्रम का आयोजन करता है. So the Board of Trustees of Hanogi Ma Mandir organizes many activities in Navaratri. That is the reference translation. So when we do the translation by original script, you can see that completely inadequate translation comes. Helicopter from children, poisonous materials, staff power, restaurant, including many complete having it. It is complete gibberish. Okay. So this is the baseline. Now, when we apply transliteration, Hanogi Ma Temple, Archi Parishad, Navaratri, or May workshop are organized. A pattern begins to emerge. Okay, a picture which is lazy begins to emerge. Now, when we go to bilingual BP embedding, plus the gloss and transliteration, then we see Hanogi Ma Mandir Archi Parishad, Navaratri में कोई कार्यशाला का आयोजन करता है. It is quite close to a fluent translation. And when we have dictionary word substitution also and transliteration, then Hanogi Ma Mandir Archi Parishad Navaratri में अनेक कार्यशालाओं का आयोजन करते हैं. This is almost perfect. Of course, we are showing a good quality output. There are absolutely terrible quality output too. But what is interesting here is that how through stages, through transliteration, through dictionary substitution, through embedding, we gradually begin to get a clear translation, which at least is going towards fluent translation. Okay, syntactic order is good, and not complete meaning transfer is happened. Because the original translation organizes many activities. The output which is obtained is organizes many workshops. Okay, workshop is not at all there in the input sentence. So meaning due to transliteration, healthy lifestyle management, adopt a healthy lifestyle. So here Hindi produces healthy lifestyle for walking art. So chal rahe hai is the word here. Chal rahe hai is not at all adequate here. It is not at all appropriate in this scenario. So chalun is walk, and Hindi translation has obtained a very literal transformation of this sentence. However, healthy lifestyle ke liye, that is a fluent part. Okay. So again, what is to be kept in mind here is that there is no parallel corpus, completely zero parallel corpus. Some simple ideas of transliteration, dictionary substitution, and making use of bilingual VP embeddings in the multilingual space are used. Okay. So this was reported in Journal of Machine Translation with extensive set of experiments to establish the ideas. I move to the last item of this whole discussion. This is phonemizer-free speech synthesis for phonetic languages. So we call this a grapheme-based TTS system, text-to-speech system. The reason for working on text-to-speech is that we are a part of a large Indian national activity on speech-to-speech machine translation. So we investigated 4 languages here: Gujarati, Hindi, Kannada, and Marathi. Kannada is from the Dravidian family, which is spoken in South India, and Gujarati, Hindi, and Marathi are from North India. Marathi is interesting because Marathi has influence from South Indian languages. Now, results suggest that phonemizers are not needed for DRD phonetic languages for the chosen architecture. So many different platforms are used for text-to-speech system. The mean opinion score, which is standard metric, which was used, and we performed mean opinion score evaluation. Native speakers were asked to rate the speech samples, like the Likert scale, 1 being worse and 5 being excellent. Each annotator rated 30 speech samples, 10 phoneme-based, 10 grapheme-based, and 10 ground truth, or 10 randomly chosen sentences, not included in the training data. So this TTS system was for these 4 languages. So let me describe what the main contribution here is. Normally, the text-to-speech systems make use of phonemizer. This is the pipeline. The text is converted to a phoneme string. Maybe most of the time it is IPA, which is generated by one of the phonemizers. We have used eSpeak phonemizer. So this converts a text string into IPA string. And from the IPA string, through other machine learning techniques, one of them being feature engineering, like Bell spectrum values. So from that, the sound is produced. So this is a standard pipeline for text to speech. What we say is that if the language is phonetic, that means grapheme to phoneme ambiguity is low. In such a case, we will not be needing this phonemizer. Okay? So this block can be completely removed, thereby reducing computation and also reducing a module which can introduce error in the pipeline. So we can directly go from text to sound. Now this is not very surprising. Okay, if the text, if the graphemes are very unambiguous with respect to phonemes, then you can directly convert the graphemes into sound symbols. So we wanted to validate this intuition. Now, what do we mean by phonetic languages? We conducted this study called phoneticity. We measured the phoneticity of the languages. So the way it was done is that we took grapheme strings, that is text strings. We took their IPA correspondences, and then we computed the entropy, which is equivalent to computing the perplexity. Okay? And we found that Gujarati, Marathi, Hindi, and Kannada have comparable amount of perplexity in them. The grapheme to phoneme ambiguity, which is a measure of entropy, is in the range of 1 for these languages. For English, it is more, 1.153. Actually, if the corpus increases, then we will see these differences to be much more significant. English should be much more, much more ambiguous language with respect to phoneticity. So we say that for Gujarati, Marathi, Hindi, Konkani, we don't need phonemizer. So again, we conducted a large number of experimentation, and these results are now under review. So for Gujarati, 10 people listened to the output speech, okay, and gave the rating. The rating was in a 1 to 5 scale, and this was processed. So we obtained a MOS score of 4.27. When we directly go from text to sound, there is very little degradation in accuracy, 4.27 to 4.24. And the ground truth was 4.34. For Marathi, which was rated by 14 listeners, the phoneme-based system gave 4.23 as the mean opinion score, and it increased for purely directly going from text to sound to 4.38. For Hindi, 4.56 to 4.55, almost same. And then for Kannada, 4.51 and 4.51, same. This shows that when we eliminate the phonemizer, which is a large-scale computation, which is a heavy resource, heavy computation, then there is hardly any accuracy drop. In fact, sometimes it increases or remains the same. So why not eliminate that module completely? So this was the intuition which was validated, and this text-to-speech module is to form part of our speech-to-speech machine translation system. Now, this study was interesting because the languages Gujarati, Marathi, Hindi, and Kannada particularly is extremely regular in its phonetic resource, grapheme to phoneme mapping. Okay. We also conducted evaluation based on other metrics like the MCD score, for example. An MCD score should be as low as possible. For Gujarati, the phoneme-based system gave an MCD score of 6.5. Grapheme-based system increased, is slightly higher, which is 6.7. For Marathi, 6.6 and 6.6 again. Hindi, 6.3, 6.3 almost. Kannada, 6.3 and 6.7. So in case of Kannada, the grapheme-based MCD score is slightly higher, 6.3 to 6.7. But the message remains the same, that when we remove the phonemizer, there is no appreciable loss in accuracy. Okay, that is the finding from this study. So now I would like to summarize my presentation. We must recognize that multilinguality is a reality, both in the virtual world and the real world. So English-centric NLP will not work for many, many languages, especially where morphological complexity is very high. Multilingual computation is the need of the hour because other languages too are demanding their legitimate space in the NLP world. And we have described in this talk our journey in the multilingual computation, starting with Wordnet, which is a very important resource linking all many languages of India. Wordnet-based cross-lingual sentiment analysis, which was shown to improve the accuracy when we operate in the meaning space. Multilingual pseudo-relevance feedback is an interesting idea where we saw that help from other languages in improving the information retrieval performance is a reality. And we described many different techniques for low resource machine translation in the multilingual world, coming back again and again to the theme of taking help from other languages, be it pivot-based machine translation or factor-based machine translation or subword-based machine translation. We take help from other languages. So the future one lies in zero-shot, few-shot, and meta-learning involving many languages of the world. Zero-shot, I have already shown some results, and we are quite intensely pursuing this line of research for Indian languages. Few-shot, wherever we have very little corpus, we make use of this corpus as well as possible. And meta-learning is where we want to adopt the machine learning model through automatic hyperparameter tuning, okay, when the language pair changes. So these ideas are being pursued in a multilingual computational work. So all these activities are done in our lab called Center for Indian Language Technology. It has been in existence since 2000, and many PhD, masters, undergraduate students have passed through this lab. So whatever I have presented is linked from this lab page as well as my own homepage. Let me finish with a demo of our speech-to-speech machine translation system. I am giving a lecture in University of Surrey. Choose the language first. Choose first English and Hindi. I am giving a lecture in University of Surrey. And Marathi quality is pretty good, but let's see English.
मैं सूर्य विश्वविद्यालय में एक व्याख्यान दे रहा हूं।
Is the sound muted?
No, if you play it, it will. Yeah.
मैं सूर्य विश्वविद्यालय में एक व्याख्यान दे रहा हूं।
People online can hear it.
People online can hear it.
Yes. This was weird because I'm hearing you.
So this room people can hear, cannot hear. Online
Because it's going on the institute.
Yeah, exactly. Yeah, I don't know if you will be able to link.
मैं सूर्य विश्वविद्यालय में एक व्याख्यान दे रहा हूँ.
So Surrey became Surrey. And this Hindi is correct. The weather at Surrey today is partly cloudy and partly sunny.
First, this will go to online.
Now, great.
आज सर्री में मौसम आंशिक रूप से तेज और पार्टिस्टन है.
Yes, sir, output is not very good.
Not very good.
Yeah. It's okay. Let's try playing.
आज सर्री में मौसम आंशिक रूप से तेज और पार्टिस्टन है.
This is gone
Yeah,
online.
again.
Yeah.
This is latest.
It's the latest.
आज सर्री में मौसम आंशिक रूप से तेज और पार्टिस्टन है.
Yeah, so this is not very good. But let's take Marathi for the same sentence. The weather at Surrey today is partly cloudy and partly sunny. Actually, it's not very good. Let me take something else. Today's lecture is on explaining language and language processing.
आज अटॉम टुडे व्याख्यानात भाषा आणि भाषा प्रक्रिया स्पष्ट करणे हे आहे.
That's quite good. So yes, so we are doing this for many different languages of the country, and it is supposed to be helpful people who are not very comfortable with English but would still like to get an idea of concepts and different subjects to cross the language barrier. Okay, thank you.
Thank you, Professor. Thank you so much for the talk. And had really beautiful insights from multilinguality, the whole NLP of Indian languages that we have been exploring for past very many years at the Center for Indian Language Technology. I'm now opening the floor to questions from anyone in the audience, and then let's open this to questions online as well. From the audience.
If there is any questions from the audience.
Constantine has raised his hand. Yeah.
Okay, in that case, Constantine, do you want to go ahead and ask?
Okay, can you hear me? Because your screen went dark now.
Stop sharing the screen.
Stop sharing. Yeah.
Okay, so thank you very much for such an interesting discussion and such a comprehensive overview of the topic. And yeah, I think you are very right that we are so privileged working with English. Yeah, it's easy, English, one language, lots of resources. But in reality, there are many other languages, and sometimes the community is forgetting about this. So thank you very much. I think the talk was very informative and brought up this issue very strongly. And yeah, I think that the whole audience benefited from this. And yeah, thank you very much for coming to university. I'm really sorry I cannot be there. Good for you, I'm not there. So yeah, this is life these days. But yeah, it is what it is. So yeah, I was fascinated about all your experiments about cross-lingual zero-shot learning, machine translation with zero-shot. And yeah, it's fantastic to see how much you can get with no training data. But I'm also thinking from the other point of view of the user. So yeah, from NLP point of view, it's fantastic that we can get from virtually nothing blur scores that are in their tens. But ultimately for the user, this is not something that they need. They need a better blur scores. So I'm just wondering, do you have any insights into properties of the languages? You actually mentioned some of this, but I'm kind of trying to tease more into this topic. How far away the languages should be in order to, or let's say how close the languages should be in order to really get some results that from the user perspective are promising.
Yeah, thank you. First of all, thank you for your kind words and thank you for inviting. And yeah, it's a pity that we cannot meet in person, but sometime in future, I'm sure. Now, this question of how close the languages should be, if you recall, Hindi, Marathi, Hindi gave a blue score of 8 and 12. Going from Hindi to Marathi, it was 8. From Marathi to Hindi, it was 12. So 8 and 12 are not so bad blue score. But yeah, you're right that the blue score should be above 20 for it to be useful for any kind of application, any kind of non-stimulus. Now, if the question is asking what more is needed to go from 8 to 20, go from 12 to 20, what other ideas can we try? So we have been quite tirelessly investigating these questions. So there are simple ideas which are low resource, for example, dictionary substitution, script substitution. Hindi Marathi, of course, have same script, but Hindi Bengali have different scripts. And Hindi Bengali have lots of vocabulary over them. So once we cross the script barrier, if both the languages are turned into the same script, then the accuracy figures will improve quite dramatically. So that we are investigating. Gujarati also has a different script. Now, for vocabulary, Gujarati, Hindi, Bengali, they all draw their vocabulary from Sanskrit and their local language, and there are local words which are found in the languages. So we have to completely exploit what is called the Tatsam category. That is the languages which are that is the words which are directly borrowed from Sanskrit. So they have to be completely exploited. Okay, so to use a common phrase, you have to extract the complete juice out of common vocabulary which is from Sanskrit. So similarly, I think these ideas will work for Italian, Romanian, French, Portuguese, where the vocabulary is drawn from Latin, for example. So first exploit the vocabulary completely, go into the common script space, and then apply dictionary substitution. So these ideas will surely help. And if we are blessed with some amount of language resource like connected Wordnets, they can also dramatically improve the zero-shot situation.
Thank you. And if there is no other question, I have another question.
Please.
A bit mean. So I was thinking about the example you gave at the beginning of your lecture, the chat with a misunderstanding.
Yes, yes.
And I'm just wondering, what chances computers have to deal with language when in a setting where you have code switching, that would probably it happens a lot in India. Humans have difficulties understanding what is being said. So I'm just wondering what level of understanding computers need to reach in order to really disambiguate when you have English words with a word in Hindi, with a few English words, maybe with an English, how is it called? The English version of the Hindi version of an English word, and so on. So you have this code switching where the two languages interact a lot. So just wondering, can we really expect at some point that computers will be able to reach the same performance on Indian texts? And when I say Indian text, including all this code switching that we report for English, and what kind of resources we would need for that?
Yeah, I think you get an excellent point. Now, so Diptesh worked on false friends, so for his PhD. Now, code mixing actually brings in false friends. Okay, so words whose sound and spelling are same, but they mean very different things. So it is interesting that we see similar kind of problems in speech, where if we use a universal phonetic repository, so some vowel sounds, some consonant sounds do not exist in another language. But if we mix the IPA corpus, for example, or the phonemes, phonetic strings of 2-3 languages together, then we have strange sound combinations. And those sound combinations are very foreign. So, so English, for example, in English, we have bank and riverbank. Two different meanings, but the same spelling. How did it happen? It happened from language contact. Most probably, the German Bank, B-A-N-Q-U-E, came to English by dropping off some phonemes and getting assimilated into the language. So now, what in code mixing, what happens is that we have mostly nominal code mixing, which means nouns get borrowed. Now, when nouns come in from English to Hindi, from Hindi to Marathi, and so on, when nouns come in, these nouns can come with the property of false friend. This noun is exactly same as another existing noun in the language, but the meanings are completely different. Okay. So in such cases, what do we do? So we really have to rely on the contextual signals. So we mix all the data, we mix the code mixed data also, and look upon the code mixed word as if it is an additional sense. So, so if ABC is a noun in Hindi, and ABC is another noun which comes from English, sounding exactly the same but different meaning, it takes us to words and disambiguation problem at a different scale. So we have an expanded words and disambiguation problem. Now the words and disambiguation problem is really solved using context, and their word embeddings have the important role to play. So here I would say that the solution lies in word embeddings, and also suffix and lemma splitting, and making use of statistical substrings like subwords in a clever way. So the noun may be same, but for a different meaning or a different part of speech, the suffixes will be different. So the suffixes will come as disambiguating signals, and that is the way. So the summary of my answer is that we look upon code mixing solution as an expanded words and disambiguation problem.
Thank you.
Any question on the chat box? We have not seen the chat box.
That shall be finished. Whatever. Oh, yes. Okay, thank you everyone for attending the talk online. Thank you the audience for being here. Uh, all the questions are over, and I think it's about time we finish the lecture. If you have any questions, please feel free to contact Prof Pushpak or me, and we'd be happy to answer them. Thank you. Thank you so much.
Thank you very much.